we have been a group that has worked together for a year and a half on this installation. We first were going to work on this via workshops where we would all get together and build the Mathemalchemy installation, of which I'm telling you in this presentation. But our first workshop was going to be in mid-March 2020. And of course, you know what happened then. The whole United States, where we're all based, shut down because of the coronavirus crisis. And we had to reorient ourselves immediately. But we did it. So it's a story not just of how the installation was made, but a story also of how all these people, none of whom knew everybody else, some of them actually met for the first time when we started building the whole thing at the start of July in 2021. And how we all hung together, how we met regularly on Zoom, how we worked together, and we joked and invented and created. We got to know each other quite well. And in fact, a year after the first online workshop, we celebrated by having an anniversary GIF card that we shared with everybody, where we alternated between pictures of everybody and an object or a scene or concept that they stood for. So this is a story of how math is beautiful, creative, fun, of people getting together to build an installation that did that, and of the solace it has given us to work on this during the whole pandemic and the companionship we got out of it. Okay, how did it all start? Well, I have been fascinated for many years by beautiful mathematical objects. Examples of these are here, just two examples that I grabbed from the gallery of the British Math and Art Association, works by George Hart and Robert Fathour. So that's one ingredient. The other ingredient is the other element that made really sparked off the whole initiative is the wonderful skills of Dominique Ehrmann, a textile artist. She made, for instance, this is one illustration of her art. She made this miniature quilt. Yes, what you see there at the very bottom is a small coin, penny-sized coin. That's how big this quilt is. And all its different pieces and the whole composition. So in order to make something like that, I don't even know how I can do that. I mean, but she is that skilled seamstress. But not just does she have the skill, she also has a fantastic imagination. Another piece of her is a windmill made out of fabric, where the different pieces rotate. And you see different views of the quilt itself as the two different wings rotate with respect to each other. I mean, just amazing. But what the first work of her that I saw was this one, Time to Break Free. Time to Break Free is an astounding artwork. I mean, the quilt itself is already beautiful. And you see here, it's inspired by some kind of steampunk machine that has the magic to transform the flat characters on the quilt into 3D figures that confidently stride into the world in order to conquer it. And I thought this was a fantastic imaginative. I mean, the workmanship is incredible, but the beauty of the whole installation and the imagination that went into it and the incredible amount of detail. So I was flabbergasted by it. So I looked her up. I didn't know about her. And I've wondered, I mean, when I saw this, I wondered, could we use that idea, that transforming machine that we saw in Time to Break Free, to maybe illustrate other transformation? And I had this idea of maybe doing a transformation of mathematical ideas that come up in one context. Like here, I imagined two little critters getting as homework, finding out whether numbers divided evenly by smaller numbers, and how the mouse that got 12 as its assignment found, yes, 2, 3, 4, 6 all work. I mean, 5 doesn't. It leaves a remainder of 2. It doesn't divide it. But the poor one that got 13, of course, finds that nothing divides it because 13 is primes. So the discovery of primes leads to the wonder, what are these special numbers? Leads to discovery of special properties of primes, like Fermat's little theorem here. The fact that if you take a prime and you take that prime power of any number at all, then when you divide it, that enormous power, because P can be huge, when you divide that enormous power by P, the prime, you'll get the same remainder as if you had divided A itself, the original number, by P, always. So that's a beautiful observation. It turns out to be at the root of some of the cryptographic machinery that we now use in open key cryptography, public key cryptography. So I thought of, could one imagine something that abstracted, showed the abstraction, and then would come out again? And I contacted Dominique Ehrmann. I didn't know her. I looked up her name. I found that she had a Facebook account, something I've never done before and very seldom since. I used Messenger to just send a message cold. And I said, you don't know me, but I was absolutely bowled over by your piece. And I'm a mathematician. There are mathematicians who are beautiful craftspeople. Would you be willing to consider designing a piece and directing a piece where different people work in order to make this installation that illustrates mathematics? And to my delight and still surprise, Dominique answered and said, yes, let's explore this, let's talk. And so we started talking. I told her, I actually gave her examples of people who are now in our team. Carolyn Yackel and her beautiful Tamari balls that illustrate algebraic symmetries. Daina Taimina and her beautiful crochet with hyperbolic properties. And Susan Goldstein, who works on both beading and knitting. And here she has an illustration of the frieze groups. These three examples I had taken from the galleries of the Bridges Association that organizes annual conferences that bring mathematics and art together. And Dominique was interested. Yes, let's do it. So we started exploring. Over the next few months, Dominique and I met weekly. We explained, we talked, we elaborated the ideas I had, and things transformed a lot already from this very vague proposition I had to something more concrete. And Dominique would try to realize things. And so ideas came up. She would make little drawings. She would show me things. She would take the examples. I would be interested already in seeing how she transformed those ideas into concrete things. I would also find that I explained mathematics to her, which was a lot of fun. So we were fascinated by the Kakeya conjecture and the beautiful figures that come out of that. It didn't make it into the final installation, maybe a future one. But so after all that, so Dominique started building a maquette. Here you see a few views of this maquette. And the maquette came, the idea was that we would take this maquette to the joint meetings in Denver, the annual meeting of the American Math Society in 2020, in January. And Dominique and I met there for the first time, even though we had talked a lot online and had our weekly meetings, we had not met in person. And we presented together at a session organized by the MAA, the Mathematical Association of America, on art and mathematics. And we launched a call. We said, look, this is a conception that we have. The piece itself will consist of many different elements. The idea is that this would not be realized by one person, but that we would have a team. So if you're interested in coming, in working on this completely different type of mathematical art than the smaller projects on which you typically work by yourself, come and join us. Come to our party. I organized a party one evening in the hotel, and people came, and it was absolutely wonderful. After that, we at the party, people signed up, and we had our first team. And then after that first evening, people said, oh, but I know such and such who would have loved to this idea, but who wasn't at the annual meetings. So could they participate too, or is it just limited? So we added, we talked to others, we added friends and friends of friends. And in the end, we ended up with our full team of 24 people. And as I said, we were going to, once we had a team together, I applied for funding. I found funding for us to have the workshops, and then the coronavirus arrived. So there was no way we could get together in person. But we decided to nevertheless still meet, have our workshop online. And during that workshop, we redesigned, we built little components, and we put things together. So we had many, many meetings where we explained to each other, where we learned about different techniques, where we sometimes chuckled at what's going on. We learned about lots of different mathematics. We sometimes were skeptical. We put together different components. Here you see the bay and the bakery. We illustrated to each other what was going on. We laughed out loud sometimes. And we gradually, the whole thing took shape. Dominique made plans and presented them to all of us. She showed different components. Others demonstrated things that had been 3D printed or embroidered. Here I'm showing off an embroidery on which I'm progressing. Here Caroline Jackel is showing off an enormous ball that's going to be a tamari ball. And here Kathy is showing how the head of the ceramic head of the baker fits on his body. So we had marvelous conversations. I mean, like, for instance, excerpts that people remember is, what motivates the chipmunks to search for devisors? The mice had become chipmunks. And of course, the tortoise has to take her lunch along when she sets out for her walk along Zeno's path. And Baker Arnold, the cat, really, his tail, should he have a tail? Because if he has a tail, it has to be covered in netting for hygienic reasons in the bakery. Let me go weigh my chickens, said Liz Paley, talking about little ceramic models that she made. And we made many, many puns. One big pun is that the nautical scene of the bay with the boat became the nautical scene. And suddenly marine life was full of knots. And here you have a couple of pictures of the nautical scene. Not the real thing. All these pictures are pictures of the second maquette that Dominique made. After we had designed everything, we took about 3 months to design, and then she made a second maquette, which is 1/4 scale, and the real thing is only being built right now. So here are pictures of the second maquette. Here are the fishermen in our nautical scene are these beautiful herons. Here are the herons on the boat. The buoys are 3D printed polytopes, but the fish are incredibly interesting fish. They are really knots because it's a nautical scene. And here you have a knotty branch with knotty things as its appendages. So that was what the nautical scene became. So we have many different scenes within the Mathemalchemy installation, and this is one of them. in the installation, we tried to bring in so many different objects and beautiful mathematical illustrations, and we used so many different techniques. It was really amazing. So let me show you just a few. So we used 3D printing, and in several different types of objects. We used beading, again, in little sea stars, and in this interesting Conway knot. We used ceramics for critters of all species, of all types. We used crochet for this beautiful octopus, but also crochet for hyperbolic surfaces. We used embroidery, we used knitting in several objects. We used laser cutting, we used steel welding, we used needle felting, origami, painting, polymer clay, quilting, sewing in several components, stained glass, tamari balls, weaving, metal welding, wire bending, woodworking in a lot of different components. If we could had a technique for which we could use, we threw it in. As a result of all those meetings in which we discussed all the things we were going to do and put in, but we also, in which we also explained all different mathematical aspects that we wanted to illustrate, Dominique learned a lot of mathematics. And she actually told us that she wished that she had known more about all the things that we were showing her prior to working on our artwork. And a result of it was that her perception of what mathematics is changed. And I think it's portrayed very nicely by how she imagined the silhouette of an adult mathematician who's looking at the whole scene changed itself. Her earlier conception was a mathematician kind of puzzled but very static, very and then her later perception was this much more fluid person who reaches out, who her clothes are flowing in the wind, so much more relatable person than I think the first one was. So I thought it was a fun side effect. Okay. I'd like to illustrate, maybe in order to give you a feeling of what went on in this whole construction, one of the scenes in more detail. I'm going to talk about the bakery. Now, we also have, apart from the bakery, we have the nautical scene, we have the garden, the coral reef, we have the curio shop, we have the roof terrace, we have the lighthouse, we have Tortoise's Walk, we have Integral Hill. So we have many, many, many scenes, and I can't explain them all, but let me go into the bakery. It all really started with the observation that standard cookie cutters are very wasteful. Why do I say that? Well, this is what cookie cutters look like, and this is how you use them. And when you make cookies, you punch out your cookies, you put them on the baking sheet, and then you have all this scrap dough. And what do you do with it? You put it together, you knead it again, or you assemble it and you roll it out again. Fine. And then you punch out more cookies. But every time you do that, in order to roll out your dough, you need to have some flour, so that dough absorbs flour every time you do this, and your dough becomes less fine. So why having to do this, all this rolling out all the time? Well, because you have the scraps around it. So why couldn't people design shapes where you wouldn't have scraps? So design cookie shapes that tile the plane. And in fact, as I was telling the others, some years ago for Pi Day, I had done exactly that. I had made pie shapes that that just fit each other nicely, so that you can punch out all your cookies without having. And I had even made cookies like that, and I made them in two different doughs so that I could make a tiling picture of the cookies in this picture. People said, "Oh, that's a great idea. We should have a bakery with such cookies." Fine. So tiling, of course, reminded Susan Goldstein of wallpaper groups. So what are wallpaper groups? Well, let me give you a demo. Let's look at a few wallpaper patterns. I borrowed them from a website made by Martin van Gagern, and he used real wallpapers to illustrate all the wallpaper groups. So let me go out of this and try to get you a wallpaper. Okay, so I have a design of an old wallpaper here. And in fact, I have the wallpaper design itself and a copy, and I triggered, you see that it's an exact copy. And it's a wallpaper, so I can, you see that if I move this exact copy around, you have, it just repeats exactly. So that's what it means to have a wallpaper copy. So a wallpaper, it repeats exactly. It would also repeat if I just moved this way. So there are two different directions where if you go by exactly the right amount, the wallpaper is invariant under what you do. So let's go back to the original. I also have, in this case, I have also a symmetry. Let's move a copy over here to the side. I don't know why I'm not seeing this. Reset. Okay, I have my copy here over on the side. On this extra one that I have here on the side, I can make a flip on that layer. I'm going to transform, going to flip it horizontally. And you see it changes a little bit because the wallpaper is not absolutely perfectly printed and so on. It's an old wallpaper, and that's how we actually see something happens. Otherwise, you wouldn't even have seen it. But you see, it was the left bird that had this little white on its shoulder, and now it's on the right because I flipped things around a vertical axis. If I undo that flip, you see. Okay, but if the wallpaper were perfect, then that would be a symmetry that it would have. It would be, it's not just something that I can translate in two directions and stays the same. I also have the symmetry. That's one of my wallpapers. Let's look at a different one. Here, again, I have that if I take this copy and I move it around by this amount, it's exactly the same. I could also have moved it around by this amount, and it would have looked exactly the same. Okay, so let's undo that. And I have this translated copy here, and I can do operations with it. It's obvious that I have a symmetry again. I mean, if I flip this, I transform it, I flip it horizontally, then it looks the same. Well, not quite. It has moved a little bit. But if I flipped it horizontally around the right axis, like for instance here, like for instance here in the middle, the line that I'm now drawing with my cursor, and it's clear that I would have complete symmetry. Okay, but I have more. I also can do vertical flips, because if I transform my layer, I flip it vertically. Oops. Again, now this one looks completely the same because it happens to be that in the middle of my figure, that's exactly, this horizontal line is exactly an axis of symmetry. If I flip it around there, I have no change. But I can do even more. I mean, let me do a transformation on this extra piece. Let me put this a center of rotation here. Then clearly after I've rotated by 90 degrees, I get the same figure again. So I have that additional symmetry. In fact, I also have other places where I can rotate. I can, if I put myself around, if I put my rotation axis here, then I don't, okay, so I put the rotation axis there. If I now rotate by 90 degrees, I don't get exactly this. Yeah, 90 degrees, I get the same. And well, if I get the same after 90 degrees, of course, I will get the same after 180 degrees as well. So you have rotation by 90 degrees and you have these symmetry axes. So it's different from the wallpaper that we saw earlier. I have yet another one here. This one, again, I have the property that I can move things and they will look the same, like here. That's one move. Or I could move things obliquely and they'll look the same. So I had a horizontal move that did it and an oblique move. So again, I have two directions in which if I move by the right amount, I get exactly the same as before. Let's look at the copy. Okay, rotations. Well, first of all, there's again a symmetry. I mean, if I transform by flipping horizontally, nothing changed. Flip horizontally, nothing much changed. But if I flip, nothing changed because I was on the wrong layer. So let me do it, transform horizontally. You see, I had a change, and again, it's because the pattern is not printed exactly symmetrically. The thick branch here has become the thick branch there because I did this horizontal flip. But it looks very similar. And if it were printed perfectly, it would look exactly the same. Let's undo, flip. Okay, if I do a vertical flip, things do change. That's a different thing. These are peace signs now instead of Y figures. So that does not, I don't have invariance under that. What if I start rotating? So let's try to rotate. Let's put ourselves center here. Clearly, this gives again the peace sign, not the Y, but if I go by 120 degrees instead of 60 degrees, I have the same old figure again. So here I have invariance, the pattern is invariant under rotations by 120 degrees. Okay, so that's different from, for these three different patterns, I have different properties. These are different wallpaper groups. It turns out that there are, in total, 17 different wallpaper groups, and you recognize the ones we saw here, the green Y figures. We had the, what else did we see? We had this particular figure, and then we had one that had invariance under this one here with the 90-degree rotation. There's 17 different wallpaper groups and no more. That's it. I mean, that's something that can be studied, proved mathematically. In particular, there are no groups for rotations. So we have rotations under 90 degrees, under 120 degrees. We have others that have rotations under 60 degrees. And we'll have some that have rotations under 180 degrees. But those are the only possibilities. So we have pi, or pi over 2, or pi over 3, or pi over 6, no pi over 5. That doesn't give rise to a wallpaper group because there are some incompatibilities there. Okay, so these are the 17. So what Susan said was we could, I mean, tiling, translation, so we could illustrate the wallpaper groups that fits with this idea of tiling, of repeating and filling the shape, filling the whole space. So she proposed to knit a wallpaper for the wallpaper groups that would illustrate these. Now, if you knit, then you can have reflection and glide symmetries very nicely represented, but not other things, because you see knitting, the knitting stitch is something that has very nice symmetry vertically, and it translates nicely, but it doesn't rotate very well. It doesn't look like itself when you rotate it. So she made a design in which the 9 wallpaper groups that have just translations and mirrorings and glide symmetries are illustrated. 9 of the 17. There remain 8. Well, 3 of those 8 have 90-degree rotation symmetry in them. Here you saw the pattern, and here is actually the finished knitted wallpaper, which is huge. It's 20 by 28 inches, and it's all double knitted. I mean, meaning it looks beautiful on both sides. It just took the negative of what you see on this side, on the other side. It was a real work of titans. Okay, what do we do with the 8 that we haven't gotten here? Well, 3 of them have 90-degree rotation symmetry, and knitting doesn't do that very well, but cross-stitching does, because cross-stitching by itself is something that has 90-degree symmetry. So Susan made 3 designs for cross-stitches, the stitch little mats that we did cross-stitch, and that will be part of the curio shop and the terrace on top of it. Then, okay, that gives us 3 of the missing 8. There's still 5 remaining. Well, those 5 have rotation of 60 or 120 degrees symmetries. So those don't lend themselves well to either knitting or stitching, cross-stitching, but they work very, very well with piecing. And so she made a little quilt design that has the remaining 5 symmetries in them. And so that will be a little wall hanging in the curio shop. So it's a beautiful illustration of how we have all the wallpaper groups, but it also exploited the different particularities of different ways of crafting and what their strengths and weaknesses are. You can also tile with non-regular polygons. And in fact, in the 70s, Marjorie Rice discovered, after reading a column by Martin Gardner in the Scientific American on mathematical games, where he reported on all the pentagonal tilings with irregular pentagons that had been found, that these were all of them, but no, they weren't. And Marjorie Rice found some extras. And so this is one of them, and we use it in order to do the floor of the bakery. It's the tile floor of the bakery, which is realized via a stitched pattern that is varnished to look like tile. But you can tile not just on the plane. This is a hyperbolic tiling, and everybody knows these figures from Escher. And Escher was actually inspired by his correspondence with Coxeter, a geometer, to make these. And they are real tilings, but of a hyperbolic plane, which means that as you go further away from the center of the disk, distance changes. But the angles are still all the same. This is a hyperbolic tiling by quadrangle. Well, they're also triangles, they're quadrangles and triangles. But the bakery has a pentagonal. We decided that the pentagon was a special figure for the bakery. I mean, we had the pentagonal tiling on the floor. So this would be a hyperbolic pentagonal tiling. And it was used in this wheel for the display card of the bakery. Here you see it standing outside the bakery. The wheel has not only this nice styling, it also has a gasket with 5 circles around the circle. So this is, you take a big circle, and then you have the central circle with the 5 bigger circles of same diameter around it. And then from then on, you just fill in every little gap by as big a circle as you can. And if you do that, you will end up, you have this gasket, you'll end up with a beautiful construction, which we combined on this wheel. The gasket reminded us of a beautiful figure from a book called Indra's Pearls, which has similar arrangements of circles, and where you then, when you do symmetries of circles, reflections of circles with respect to circles, you actually find that you build implicitly another gasket. The yellow lines on this are built by that. It's a beautiful book. I recommend it. You really should look at it if you're intrigued by this kind of thing. So we decided we would try to see if we used 5 circles, what we would get, and this built a beautiful figure that we liked very much, with all these reflections of circles with respect to each other, that we used in order to make the cast iron door for the oven in the bakery. So the bakery has all these different geometric constructions in it. Now, in the reflections, I was doing reflections of circles over and over again. So that's iterated maps. And that actually is how we ended up with our baker, who is a cat. How did that come about? Well, there is something that's called a baker's transformation. If you start, so we're now thinking of maps that take, let's say, a rectangle and map it to itself. One way of doing that is to take the rectangle and flatten it so that it becomes twice as long, but only half as high. Cut it in 2, fold this over, and you have a rectangle of the same original size. So you start from this big cat here at the top and end up with the cat at the bottom. Actually, the baker's transformation, as mathematicians do it, really doesn't have the folding over. That's what bakers really do, and that's why I wanted to draw it this way. Bakers do fold over and so roll out and fold. Typically, I fold in 3, actually, but in the mathematical simplification is to just cut it in 2 and put one on top of the other. Why did I choose the cat? Well, because the baker's transformation was originally so a map of a rectangle to itself was originally proposed with a slightly different, more complicated version that has the same property of mixing things up. You see, the property here is that when you do this many, many times with your cat, then instead of having this black figure on white ground, you end up with something that's gray all over. Things get mixed very much, and that's a property, it's called the mixing property of this map. So an earlier map that had been proposed and that has a mixing property had been proposed by a mathematician called Vladimir Arnold, a Russian mathematician. So he said, let's stretch in one direction and it automatically compresses in the other direction so that we keep the same area. Now, what means is you have left your original rectangle, but if you now imagine taking just what is sitting into the next rectangle over in red, or the next rectangle to the right of that in beige, or then a rectangle on top of that in blue, then you can just move those pieces back. I mean, the red one, for instance, moves back to the corner here, the beige one to the upper corner, and then what you're missing is exactly that little blue map. And so because the area was preserved, you have a way of mapping the original cat to this kind of scrambled cat. And he showed this figure with a cat. And because his name was Vladimir Arnold, everybody called this Arnold's cat. You can look up Arnold's cat in Wikipedia and you will find this figure. So when we had decided we were going to look at iterated maps, it was obvious that we were going to have a cat, and the cat was going to be called Arnold. So our baker is a cat, and he's called Arnold. And he's assisted by his friend, Mouse, because cat and mouse, of course, but also Arnold and Moser did work together. And there's a famous construction mathematics that's called Kolmogorov-Arnold Moser. And so it seemed natural to have Arnold and Mose in the bakery. Here is the bakery. You see pentagons all over. It's really beautiful. It also has here an illustration above the door of a periodic orbit in the pentagon. I mean, imagine having a billiard with a pentagonal border and shooting a billiard ball that gets reflected all the time. Well, if you have a perfect billiard ball that's never slowed down by friction, and you choose your angle well, then it will, after many, many turns, end up in exactly the same position with the same velocity as before. So it's a periodic orbit. After many turns, it will repeat its orbit. Bakery again, it's this beautiful object. Now, the bakery, of course, is known for a very special cookie it bakes, kind of biscotti with almonds. Those are also called Mandelbrot, because Mandelbrot, of course, is a mathematician. The Mandelbrot set is linked to iterated maps. So you see here how one simple idea led to many, many different things in this bakery, which are all there. And I haven't even described all of them. You'll have to come and see it, the piece, when it's finished. The adventure continues, and we are building it as I speak. And at the end, I will show you some pictures of how we're building it now. I would like to end by thanking all the other members of the Mathemalchemy team. It's been an exciting, wonderful adventure for me, and it continues because we're building right now. Here you see all their pictures again and their names. Most of us are mathematicians. The M stands for mathematician. If I had spelled that out in full, then I would have had to go to a smaller font, and I want you to see their names. But we also have an engineer and an architect and a physicist and a manager. We cover a wide range of bases. It's been a fantastic collaboration. The collaborative nature of the whole adventure is what made it special and is what made it so exhilarating to all of us. So thank you, all of you. And as I said, we are building it right now. So in the final instance of this lecture, we'll share some pictures of the installation as it was taking place on July 2nd. But we're building, and we'll be building until nearly the end of July, when the whole thing will be complete. For real now, in scale, 1:1, no longer 1:8, 1:4, 1:4, 1:1. The big installation. And we'll see it for real. And it's, I expect, as wonderful as we hope it will be. Thank you.